Hey guys, this is Black. Welcome back to the YouTube channel. In this video, we will discuss about Java Virtual Machine JVM. What is Java Virtual Machine? JVM is a virtual machine that enables a computer to run Java programs and provide a runtime environment for Java code to be executed. The JVM interprets Java bytecode and translates it into a machine code that can be executed by the host system. This allows Java applications to be platform independent as they can run on any device with a compatible JVM. JVM plays a crucial role in making Java a versatile, portable, and secure programming language. Different implementation of the JVM exist, such as Oracle Hotspot, OpenJ9, and Graal IVM, each with its own optimization and features. This is the JVM architecture. Now we will discuss each component of the JVM architecture. JVM class loader. Class loader is responsible for loading classes into memory during runtime. Here are the key points about class loaders. Loading classes. Class loaders load Java classes into the JVM when they are first referenced in a program. This process involves locating the class file, reading its bytecode, and creating a representation of the class in the JVM's memory. Hierarchy. Class loaders follow a hierarchical structure. The Bootstrap class loader, implemented in native code, loads core Java classes. Extension class loader loads classes from the extension directory. An application class loader loads classes from the class path, including user-defined classes. Delegation model. Class loaders typically follow a delegation model, where a class loader delegates the class loading request to its parent before attempting to load the class itself. This hierarchy ensures that classes are loaded only once and promotes a modular and efficient loading process. Class loader types. Java supports different types of class loaders such as Bootstrap class loader, extension class loader, and application class loader. Additionally, developers can create custom class loaders to implement specific loading behavior, such as loading classes from a network or database. Dynamic class loading. Class loaders enable dynamic class loading at runtime. This flexibility is particularly useful in scenarios where the classes to be loaded are not known until the program is running, allowing for its extensibility and adaptability. JVM class area. In the Java virtual machine, the class area, also known as method area, is a part of memory used for storing class-related information and metadata. Here are key aspects of the class area. Storage of class information. The class area is responsible for storing class metadata, static fields, and method information. It is shared among all threads and represents the runtime representation of loaded classes. Static fields. Static fields associated with a class are stored in class area. These fields are shared among all instances of the class. Constant pool. The class area contains the constant pool, which is a table of symbolic references and constants used in a class. It includes information about methods, fields, and class references. Method information. Information about methods such as method bytecode, method signatures, and other related data is stored in the class area. This allows the JVM to execute methods as needed. Class loading. The process of loading classes into memory is managed by the class loader, and the loaded classes are stored in the class area. The class loading process involves locating the class file, reading its bytecode, and creating a runtime representation of the class. Shared among threads. Unlike the heap, which is used for storing objects and is thread specific, the class area is shared among all threads running within the JVM. This ensures that class-related information is consistent across the application. JVM heap. In the Java virtual machine, the heap is the region of memory used for dynamic memory allocation. Here are key points about the heap. Object storage. The heap is primarily used to store objects created during the execution of a Java program. Objects in Java include instance of classes, arrays, and other data structures. Dynamic memory allocation. Unlike the stack, which stores local variables and method call information, the heap is used for allocating memory dynamically at runtime. Objects on the heap are not limited to a specific scope or lifetime, making them suitable for data that needs to persist beyond a single method invocation. Garbage collection. The JVM's garbage collector is responsible for reclaiming memory occupied by objects that are no longer reachable or in use. This process helps prevent memory leaks and efficiently manage the available memory in the heap. Generational model. The heap is often divided into two main areas, the young generation and the old generation. The young generation is where new objects are initially allocated, and the old generation is where objects that survive multiple garbage collection cycles are eventually moved. This generational model optimizes garbage collection efficiency. Java heap size. The size of the heap can be configured using JVM command line options. It includes parameters such as initial heap size, maximum heap size, and the garbage collection options. Properly tuning these parameters is essential for optimizing the performance of Java application. Out of memory error. When the heap is unable to allocate enough memory for new objects, an out of memory error is thrown, indicating that application has exhausted its available heap space. JVM stack. In the Java virtual machine, the stack is a region of memory used for execution of threads. Here are key points about the stack. Thread specific memory. Each thread running in the JVM has its own private stack. The stack is used to store local variables, method call information, and partial results. Method execution. When a method is invoked, a new frame is pushed into the thread stack. This frame contains the method's local variables, operand stack, and other information needed for the method's execution. LIFO structure. The stack operates on an last in first out basis, meaning that the last method call made is the first one to be completed. As method finish execution, their frames are popped off the stack. Local variables. The stack holds local variables for each method. Local variables are specific to the current method invocation and are used for storing temporary data during the method execution. Operand stack. The operand stack, also known as execution stack, is used to perform operations such as arithmetic calculations. It holds values pushed onto the stack during the method execution. Stack overflow. If the stack runs out of space due to excessive method invocations or a very deep recursion, a stack overflow error is thrown, indicating that the stack has reached its limit. Memory efficiency. The stack memory is efficient because it's managed on per thread basis, and the memory is automatically reclaimed when a method finishes execution. No garbage collection. Unlike the heap, the stack is not involved in garbage collection. Memory used by the stack is automatically reclaimed when a method completes, making it more straightforward in terms of memory management. JVM's other components. Program counter register. Program counter register contains the address of Java virtual machine instruction currently being executed. Native method stack. It contains all the native methods used in the application. Execution engine. It contains a virtual processor, interpreter. The interpreter reads bytecode stream, then executes the instructions. Just-in-time JIT compiler. It is used to improve the performance. JIT compiles parts of bytecode that have similar functionality at the same time, and hence reduces the amount of time needed for compilation. Here, the term compiler refers to a translator from the instruction set of a Java virtual machine to the instruction set of a specific CPU. Java Native Interface. Java Native Interface is a framework which provides an interface to communicate with other applications written in other languages like C, C++, assembly, etc. Java uses JNI framework to send output to the console or interact with OS libraries. That's it for the video, guys. If you enjoy the content, like the video and subscribe to my YouTube channel. See you on the next video. Bye bye.